Hello and welcome to this optional video that handles some current unanswered questions. Since I made one of these videos before, I'm calling this one Unanswered Questions Part 2. And you probably have more questions bothering you right now than these 5, but I think what we'll do in this video is focus on questions 1 and 3 and maybe address question 5. But okay, so again, I want to emphasize, re-emphasize that this video is optional. So this is optional. Most of you have plenty of demands on your time right now, so perhaps you can use this video to fall asleep. Perhaps you're kind of curious why the fundamental theorems of calculus parts 1 and 2 are true. Perhaps you've always been curious. Oh, wait. I don't think I'm going to answer number 3. I think the answer is there. I think it's yes. The department is having exams. What I meant was 1 and 4. Anyways, so this is an optional video that might be of interest to those who are a little curious about where the fundamental theorem of calculus parts 1 and 2 come from, how they work. But okay, so let's start with, well, first let me give myself some more sheets of paper. Who knows how many I'll need. Let's see. There we go. Well, that's probably enough. Okay, so let's maybe start with the fundamental theorem of calculus, part 1. And so here's what the fundamental theorem of calculus, part 1 was telling us, that if you form this area accumulation function, capital F of x, starting at some point A and ending at the stopping point x, and if you add up all of little f's information, then the derivative of this is just the integrand little f. So there are some conditions on little f, and I'm going to use them here in explaining why this is true. Right? This actually isn't that bad, so the conditions will come out soon. So why is this true? Why is the derivative of area accumulation the original function? Well, first let me give you the sort of, if you will, detailed explanation. It's not that detailed. Let's just go back to what the derivative means. And it's a limit, right, as h goes to 0 of a change in output values divided by a change in input values. So that's where I'm going to start. I'm going to start looking at this expression, capital F of x. I'm going to look at capital F of x plus h. And so this will be the integral from a to this new number, x plus h, of little f. And, of course, capital F of x is just the integral from a to x plus h of little f. And we already know how to combine these two expressions, but I just want to remind you visually where this comes from. So if I make a little pretend graph over here, call this the t-axis, and maybe my graph of little f of t looks something like this, then this first integral starts at a and ends over here at x plus h, whereas that second integral, capital F of x, ends at x. Right, so the first integral represents more area than the second integral, capital F of x, and so if you subtract those two areas, what you're computing is the area of this little part. And so when we do that, when I write capital F of x plus h minus capital F of x, that's just adding up all that area starting at x and ending at x plus h. of my function little f. That's it. That's all that's happening there. And so now to get a handle on this guy's derivative, right, I'm going to divide him by h, which is the same thing as multiplying by 1 over h. And now I want to sort of manipulate this expression before I let h go to 0. And it's actually not too hard to manipulate this. Here's where I'm finally going to use some hypotheses, some conditions. Since the function little f is continuous, it's continuous on this interval I'm looking at, on the interval from the starting point x to the new stopping point x plus h. It has a maximum value, capital M, and a minimum value, lowercase m. And maybe if I zoom in a little bit and go to this picture, right on this interval, here's its capital M value, it's a maximum there, and here's its lowercase minimal value. Okay, so what we're really saying here is that the function f of t on this interval is bounded above by some maximum value and bounded below by some minimum value. That just happens because it's continuous. It's not allowed to jump across values or have an asymptote, so it's bounded. And now, what we really have is this fraction that we're about to take a limit of as h goes to 0. Well, this integral is bounded by capital M, so I'll have capital M, and then I'll have that 1 over h, times the integral from x to x plus h of just 1 dt. And if you let me simplify that, that'll just be the length of the integral, that's just h. Similarly, this integral is bounded below, right, by little m, and I've got that over h, and then times the length of the interval, and so those h's all cancel, and what I'm actually left with is this. This area accumulation function, when I form this, some people call it a difference quotient, when I form this difference quotient, it's bounded above by this number capital M, and it's bounded below by this number lowercase m, just like the original function f is. Which makes us think this difference quotient is behaving more and more like f. And here's the trick. As h goes to 0, this fraction, by definition, turns into the derivative. And so what we want to think about, as h goes to 0, what do these two things turn into? And if you look at our picture, maybe I'll zoom in again. In our picture, if h goes to 0, then this interval is shrinking this way. Right? There are fewer and fewer points in this interval if h is going to 0. And so what's happening to our maximum value m and our minimum value m? As h goes to 0, capital M equals m, there's just one place where the function can achieve this information, just at the one point that's left as h goes to 0. So as h goes to 0, this capital M and lowercase m turn into, capital M turns into, and lowercase m turns into just f of x. And so what that tells us is we have that f prime of x, right? That's the limit of that fraction I circled as h goes to 0. It turns into something less than little f of x and something bigger than little f of x. Well, there's only one way to be a number trapped above and below by the same number. You've got to actually equal this value. So that's how most textbooks will try to explain the fundamental theorem of calculus part 1. And I will admit, it always feels at least a little bit clunky, and the reason is that our function, f of x here, is defined in a complicated way. It's defined by adding up another function. And so to manipulate that guy according to the definition of a derivative, it's going to take some careful work. Okay, so that was one reason to believe the fundamental theorem of calculus part 1. Let me go on to the fundamental theorem of calculus part 2. This one I actually, I can use my proof for part 1, but I'm going to use a different proof because I really like this other way of explaining it. So let's recall what this says. It says if you're integrating from a to b the values of a function, then it has to equal using an antiderivative. And so I just want to point something out. The fundamental theorem of calculus part 2 is so useful, right? It lets us skip over using rectangles to approximate signed area. And yet we give you no explanation in this course as to why you can skip the rectangle way of doing it and jump straight to using an antiderivative. And my thinking personally is, well, if we're not going to tell you or give you any hint as to why did we even tell you about the rectangles to begin with? Why didn't we just tell you to do this way? In any event, so here's where we're going to start. Let's start. So like, why is this true? Well, let's start with the fact that we have this function little f of x, and we have an antiderivative for it, right? That's what this is really saying. If you know an antiderivative, if you know this, then you can evaluate this stuff. So let's start there. Let's say, okay, suppose I know this. And here's what I'm going to do. I'm going to say that the definite integral of f of x dx, I'm going to admit, you know what? This is a limit of a bunch of rectangle area. Yeah, so might be something like, so that sum stops at m, might be something like f of xi times like some weird delta x, right? And here, right, this was what we sort of rehearsed talking about. We just practiced doing this process from section 6.1, where we didn't let n get big. We stopped n at like 3 or 4 and said that was an approximation. Part of our process, though, for that was to say, we can pick whatever we want here. We can pick these however we want. Now, we showed you in 6.1 3 popular choices. We could pick left endpoints, right points, or midpoints. Those were really common. Here's what I'm going to do, though. I'm going to pick these. I'm going to select what I'm calling the x sub i's, like in a different way. Differently. I'm not going to pick left points or right points or midpoints. In fact, you're allowed, it turns out this definition of integrating, right, of setting up rectangles and taking these limits is super powerful. It doesn't matter how you pick these points to plug in to get your heights, right? You can pick them using the upper sum or lower sum rule. You can pick them using left points, right points, midpoints. You can literally pick them randomly. You can get drunk and just throw a dart at each little sub-interval and pick an xi to create a height for your rectangle. You can do that as when n is 10, when n is a million, right? Do that over and over and over again. I guess that's not a very healthy choice, but the integral will still work. And so here's the truth. We should be really clever in how we pick these things. I'm going to select these. I'm going to choose each x sub I so that the mean value theorem works. Let me tell you what I mean here. We already said from the beginning f was somebody's derivative. We're starting with knowing that. And I'm saying, oh, hey, this looks like the answer to a mean value theorem, right? If this were g prime of c, this would be g of b minus g of a all divided by b minus a. That would be the mean value theorem. Well, here, what's playing the role of c is this xi, and what I have here are two endpoints. I'll say bi minus g of ai all over bi minus ai. Well, that's delta x. So what's really going on is I have partitioned up my interval from a to b into a bunch of things, right? And what I want to do is don't pick a left endpoint, don't pick a right endpoint, don't pick a midpoint, pick some point. I can't even tell you exactly where it is, but at some point, maybe it's there for the first one, so that f of xi equals this fraction. And so now, look what happens when I set all that up. I have that my definite integral from a to b of f of x dx is a limit, as my number of rectangles gets really, really big, of these heights. So it was f of xi times the delta x. And then I say, okay, but I am telling you, pick those xi's so that those heights have this nice form that the mean value theorem tells me to use. And notice, I'm using the mean value theorem on these n intervals. So I'm really doing the mean value theorem n times. So now I get to write here something like g of bi minus g of ai, all divided by the width of that particular subinterval. Well, these terms cancel, and you get something that mathematicians love. It's called a telescoping sum. So I'll write it out, and then I'll write out a few terms to show you why it's so lovely. So I have something like g of bi minus g of ai. And here's the idea. What this ends up looking like is something like this. So my last one that'll appear will be like g of b. Let's see if I can use my picture over here. So it'll be g of b minus this one, right? Let's just call that, oh, for the moment, let's call that z for a second. Minus g of z, right? So that would be the mean value theorem happening right here. But then what happened on the interval right before it? Well, right there on that interval, I had picked it so that f of xi became g of z minus, and now I need a name for this guy, maybe I'll call it w, g of w, right? So on the one right before it, there was a plus g of z minus g of w. I've run out of room. But the point still is that these two have to cancel. So let me put in some dots. Dot, dot, dot. And then even over here, if I keep this process going, right, what happened on the interval right next to w? Well, on that interval, I would have had a g of w minus g of this point. And so the w's would cancel. And so the point is, all the terms in this long sum completely cancel when you use the mean value theorem on each interval. So the only thing that survives is the g of b at the beginning, and then a bunch of this g of w cancels with something, and then something. The only thing left over is g of a. So everything cancels. I call it a telescoping sum because like one of those old telescopes that you could maybe carry around on a ship or something, you could push it down, sort of fold it down, so all the intermediate terms get pushed away. They cancel out. Notice there's no in this anymore. There's just two terms. So this is like taking a limit of something that's constant, and what you get is exactly what we said you would get from the statement of this theorem, part 2. Right. One thing I want to point out, though, again, I secretly used that little f was continuous when I invoked the mean value theorem. Okay, so those are sort of two quick explanations, and I'll just summarize them here because the details I tried to offer I don't think were the greatest there, but fundamental theorem of calculus explanations summary. These were sort of my two quick attempts. For part 1, we carefully manipulate this integral definition. Right, so we form this thing and looked at it very carefully. And we use the fact that f is continuous and therefore bounded. As h went to 0, those bounds became the same number. Those were sort of the ingredients. For part 2, what we used was the limit definition in terms of rectangles. So I'll just say rectangles. And then we use the mean value theorem to make terms cancel. And all of that worked out to give us both of these. And now what I'd like to do is maybe address briefly question 5 that I had up there, which is like, what is the point of any of this? And or is there a point? And the answer is no. But, well, I don't know. I just mean that in general. But what I'd really like to do is give you a more basic, and by basic I don't mean dumb, I mean great, a more basic understanding of the fundamental theorem of calculus. And so notice now I'm not even referring to it as two parts. So whenever I talk about the fundamental theorem of calculus, what I'm saying is, why should we believe that differentiation and integration are opposites? That's really what parts 1 and 2 together say. I think opposites has 1t. Whatever. Okay. So this is going to be pretty quick, and we could have done this at the very beginning of the semester. So let's think about this. Well, what is the derivative of a function? If you really think about this, right? Sure, it's a limit as h goes to 0 of f of x plus h minus f of x all divided by h. And I could, I'll remind you where this came from, because there are a couple other ways we could have written this, but we could have done f of x plus h minus f of x, and that's all over x plus h minus x. Okay, what was our motivation for setting up this limit? Our motivation was to say, we want to get this slope of this line we can sort of picture. And if you hide, right, if you hide up the h going to 0 part, this is exactly what this fraction is. It's take a difference in y values and divide it by a difference in x values. The key thing, right, was that we needed to let the limit, we needed to let h go to 0. We needed to take a limit. And now let's think about, just sort of roughly in symbols, what is an integral? And again, it's going to be a limit as something, not going to 0, it's going to infinity, but it's a bunch of adding, right? It stops at n. I'll even say, let's put an I there. F of xi, those are your different heights, right? You're plugging in different xi's times maybe a common width. And our motivation for setting up that monstrosity was to try and approximate curvy area. Okay, but now let's just look at this. Let's think about what's going into each piece. Into the first one up here on the right, what do we have? We have into this, so let me make a little dividing line. Into this first one up here, we have step 1. First, we're going to, let's see, I want to say this really, really carefully. Step 1, we first subtract, right? So we subtract some y values, and then step 2 is we divide by a change in x. And what's going on over here with the definite integral? Well, the first thing we're doing is multiplying, right? Right, we're doing a height times a width, and then the second thing we're doing is adding. Okay, and then we take a limit. It's true in both, but ignoring the limit for both of these, look at these processes. What is the opposite of adding? The opposite of adding is, of course, subtracting. And what's the opposite of dividing? The opposite of dividing is multiplying. Taking a derivative is made up of 3 things: subtracting, dividing, taking a limit. Taking an integral, computing some signed area, is made up of 3 things: multiplying, adding, taking a limit. And if I ignore the limits for a second, look, the key ingredients into both processes are complete opposites. Not only that, they're not just opposite processes, but they're in opposite order. Right? Taking a derivative says step 1, subtract, step 2, divide. Computing assigned area flips the order and makes opposite those flip steps. It says, okay, don't do dividing first, do the opposite. Sorry, it says don't do dividing second, do the opposite of dividing first, and then do the opposite of subtracting second. And then take a limit. So when you view from like this, when you take this view from like 50,000 feet above, of course, integrals and derivatives are opposite. They are made up of opposite steps arranged with respect to the other in reverse order. Deep down in your bones, it shouldn't be surprising that integrating and differentiating are opposite, because deep down in your bones, you know that adding and subtracting are opposite, and dividing and multiplying are opposite. So it turns out trying to compute a derivative is trying to answer a different sort of question than trying to compute an integral. Trying to compute a derivative is all about looking at slopes. Trying to compute an integral is all about looking at areas. These two things have nothing to do with one another until you write them out in terms of their component steps. One involves subtract as step 1, one involves add as step 2. The first involves divide as step 1, The second involves multiply as step 2. And then they both have limits. So what was this gigantic story of Calculus 1 really all about? Calculus, just to sort of put a bow on all of this, started off like this. We want you to learn limits, or at least we want you to get comfortable with them. And then limits turned into, we use those to build derivatives. So what did we combine with limits? Well, we did subtracting and then dividing. And then we took a limit of that to get derivatives. Then we did a whole bunch of work this semester on applications of derivatives, a whole bunch of stuff that made you happy, that made you angry, that made you sad. Okay, and then for the last few weeks of class, we switch and we say, not only can we use limits to talk about derivatives, we can use limits to talk about integrals, which helps us compute areas. And we say, well, to set up what an area is, we'll use rectangles, and to set up rectangles, that's when we're going to multiply a height and a width, and then we're going to add up all those rectangle areas. And then you compare these two things and you say, hey, these are of course made up of opposite pieces. They both have a limit. These two things undo each other. And that's the fundamental theorem of calculus. All right, so hopefully that was interesting enough. If not, that's okay. This won't be tested, at least not in the way that I've presented it. I hope you guys are doing well, and I'll talk to you another time.